In a circuit in AC steady state, all the voltages and all the currents have the same frequency, omega radians per second. In Canada and the United States, that frequency is 377 radians per second. In Europe, is 314 radians per second approximately. Today we will see that the power is also changing sinusoidally with time, but with twice the frequency. Power in its oscillation in time, sometimes it is positive, part of the time it is negative. So we have a system that is absorbing power part of the time and is delivering power part of the time. Consider that box, that element. That box represents part of a circuit. Could be a resistor, an inductor, a capacitor, a combination of them. Could be a whole residential building, could be an industrial building, a neighborhood, a whole city. Could be part of the country, could be part of the continent. Whatever that is, that box, it has a voltage applied to that is sinusoidal like this one. The voltage has an RMS volts V, and it has an angular frequency omega, which is 377 radians per second in North America, and a phase shift alpha radians with respect to a chosen reference for phases. The current in that element is also sinusoidal and it has the same frequency. That current in that element has an RMS value I, the same angular frequency, and a different phase shift beta radians. If we want to find what is the power, we can do that point by point along the time axis, like multiplying those two time functions like this. The power absorbed is a convention. Absorbed power is VI. Multiply that, and this is the expression. We say this gives us the power absorbed by that element point by point in time. It is evidently a function of time. Let's simplify that expression. I copy that expression here, and then remember this trigonometric expression of the sum of two angles and apply that over here and over there. We expand those signs of omega t plus alpha and omega t plus beta and multiply and add and simplify, and we get this humongous expression. Let's copy that on to the next slide over here, and then we're going to use another set of equivalences we saw in high school. The square of the sine of x, the square of the cosine of x, and the product of sine of x with cosine of x. All of those depend on trigonometric functions of twice that x angle. Let's apply this square sine formula here, the square cosine formula there, and the sine x cosine x formula over there. We do that, reorganize, simplify, and the expression for the instantaneous power in that element becomes this. VI. V is the RMS value of the voltage, I is the RMS value of the current, alpha is the phase shift of the voltage, beta is the phase shift of the current, etc. Observe that the power, the instantaneous power, is a function of time. You can see that here, t. But the average of that power is the average of this constant plus the average of this cosine. You and I know that the average of the cosine is 0. So the average of the power is just this term. It is a constant and a function of time. I repeat, the average of that power is just this term, the average power, the one that utilities will charge the customer for. RMSV, RMSI, and the cosine of the difference of phases between the voltage and the current. We call that angle, that difference angle, usually theta, the power factor angle of that load. What about this term? Well, this term is cosine, has an average 0, right? Average power, which we call the active power, is given like that. Graphically, we see that active power or average power is the product of the RMS value of the voltage, the RMS value of the current, and the cosine of the angle between them two, theta, the power factor angle. Graphically, We could say something like that. If the black curve is representing the voltage and the blue curve represents the current in the element, we observe that the current is slightly lagged behind the voltage by a little angle here, so it's slightly inductive. When we multiply them, we get the power as a function of time, absorbed power by the element, which is positive most of the time. The element is absorbing positive power. And between this point and that point, the power is negative. The absorbed power is negative. So we say between this point and that point, the element is actually delivering power. Let's recap. Between this point and that point, the element is absorbing positive power. And between this point and this point, the element is absorbing negative power. So it is absorbing power and then it's delivering power back. It takes power from the source and then it returns power to the source. Do we remember that the area under the power curve with respect to time is the energy transmitted? So this area, this big area here, is actually the energy absorbed by the element between this point in time and this other point in time. What about the area of this little peak of negative power here? That is the energy returned by the element to the generators, to the source. So in every power cycle, from here to there, the element is going to receive all of this energy represented by the big area, and it's going to be returning a little bit of the energy back to the generator. So it's taking a huge amount of power and it's playing ping pong with the generator with this amount of power. Every cycle, every power cycle, it's taking that amount of power and returning it back to the generator. So in average, that energy is going back and forth between the load and the generator. Is like a ping pong energy. The average of that, the average power, is the one given by the formula we saw. And then we have power associated with this ping pong energy. We call that reactive power. Reactive power and active power. This is the one the power utility charges the customer for. And the reactive power, the customer will say, oh, you cannot charge me for that because after all, that is energy that I'm returning to you every power cycle. Oh, yeah, right. Let's introduce now the concept of apparent power, represented with a letter, the uppercase letter S. IC voltmeters and ammeters, they read effective values, RMS volts and RMS amps, V and I. Apparent power is a real number. It's just the multiplication of the reading of the voltmeter times the reading of the ammeter. So it's a very easy to obtain number. The units are VAs, volt amperes. Unit-wise, the unit VA is just a watt. But so the engineer realizes that the number is not actually power, average power, but apparent power, just the multiplication of the voltmeter reading and the ammeter reading. We call that VAs. And if there are too many, we say kVA, kilovolt amperes or megavolt amperes. Let's talk now of the average power. We call that active power. That is the average power in watts, and it VI cosine theta, RMS volts, RMS amps, and the cosine of the phase difference between the voltage and the current that you see here. Observe that the active power is only a percentage of the apparent power VI, and the percentage is given by that cosine. And that percentage, of course, is going to be less or equal than 1. The percentage of the apparent power that becomes active power is that power factor, cosine of theta. And that is the name, and that is a concept that we introduced right now. Power factor, cosine of the angle of the voltage minus the angle of the current. Or should I say more properly, phase of the voltage minus phase of the current. What about that ping pong energy? There is some energy traveling back and forth between the load and the generators. So if you average that with respect to time, you get some power. We call that reactive power. Informally, only in this course, we're going to call that ping pong power. But the proper name is reactive power. Q. This is related, as I said, to the ping pong energy, and the average is VI, the apparent power, times sine of the same angle theta. The reactive power is also proportional to the apparent power VI, but through a different factor. The units of Q are volt ampere reactive. Again, unit-wise, they are watts. VAR is only a convention to say that this is not average power, but is the reactive power.